DNS is one of the oldest protocols on the internet. It's a very successful one. In its most used form, it translates names like google.com to IP addresses. So you type in your browser google.com, then DNS plays a role there before the IP protocol takes it over. There is a very good analogy for this. It is phone books, although phone books are not very common anymore. So the phone numbers are IP addresses, and the names are the people's names are the domain names. So this analogy goes pretty far. So you don't what you have to type in your phone are phone numbers, and same for the internet. You need IP addresses. That's where you can send packets, and one person can have multiple phone numbers. They can change their phone numbers, but you still want to call your friend. It's by his name or her name. That yeah. So for that level, this is where it is used mostly. On that level, this phone book analogy is pretty good. But what else DNS is good for? If you worked long enough as a software engineer, then you probably migrated a lot of things from one place to another. So big applications migrating from on-prem to cloud, for example, and then your DNS is a very major tool in your toolbox there. You can change the underlying infrastructure below the DNS. So you have a stable DNS name where you through that you call some service, and then if you make your migration well, then the clients of that service will not notice that you migrated. DNS is your major tool there. But what else can DNS do? For example, load balancing. So if you have a worldwide service, then your DNS queries, your DNS server might answer based on the location of your client differently. So for example, if your client is in Europe, then it will answer an IP address that is an IP of a server in Europe, but differently in the US. This is one level. So this is the first front for load balancing a global service. What else? For example, you can answer with multiple IP addresses, and then your clients on the client side can randomly pick one of them and call that one. This is not a perfect load balancing, but it's if you have a lot of clients, then it still does something for you. Of course, you have to do much better load balancing in your actual server. Okay, that's enough talk for now. Let's write something. One of the most basic tools to query DNS is called dig. It is available for every machine, I think. It is part of a suite. I think a DNS suite. It's from Bind, I think. But it can be, you can get it separately from the big package. So in this most basic form, we query for an A record for a domain name, and then we got a very cryptic answer. There are tons of things here that are a bit strange. So basically, this is the line we were looking for, and our goal was to get this IP address only. Of course, there is a short format for dig where you can get only this one, but I think this is interesting. What are these other stuff? Let's dig deeper into this in this video. So here is the name. An interesting stuff that you can notice is that there is a dot after it. This actually has a meaning. This is the root servers of DNS. I will talk about this later. So this is not just a strange thing. It actually has a meaning. This number is a TTL. TTL is how long it lives. This is in seconds. So if you call it again, then it already decreased a bit. It has a very short TTL, so this means that Google uses DNS dynamically. They are doing some tricks with it. If this would be like 2 weeks long, then they would. Yeah, so this tells a bit about Google, that Google is doing something, but not about what they are doing. In is internet. I don't think you will ever encounter a DNS query where it is not about the internet, but it was designed as to be extendable. A is the most common resource record type. It means IPv6. There are other record types like AA for IPv6. Sorry, A is for IPv4. A is for IPv6. There are. Okay, let's list a few common resource records. That CNAME is a canonical name. When, for example, google.com could be CNAME to somewhere else, like Microsoft.com. That will never happen, but then your yeah, actually CNAME is a bit complicated. Anyway, if you would query for google.com, then you will see actually two answers. Here there will be a first line will be a CNAME to Microsoft.com, and then an answer section for Microsoft.com and an IPv address. But yeah, normally that's not unless you would query specifically for a CNAME. If you are querying for an A record, that's what would happen. Okay, a CNAME is actually a bit special. There are things like text records. No, it's actually. Oh, what did I do? Okay, there are things like text records and a bunch of others, like for DNSSEC and. Okay, I will not list them. There are around 100 different resource records. So DNS is actually a extensible protocol, and you can query for different things, not just for IPv addresses. These things you are querying for are called resource records, and you can wrap many things inside resource records. Some got deprecated over time, but you were for example able to query the operating system of the machine and things like that. You are querying by name, by a domain name. There are some rules about the domain name. We will see that a bit later. Let's take a peek into the internals of what DIG is doing. The most effective way to do this is by strace, where we can look at all the system calls, how this binary communicated with the kernel. We are looking for basically the socket communication and grab the messages there. That's our goal. So we will call dig google.com just like before, but we are calling it through via strace. We send the -f here because it will use multiple processes, I think, or threads. Anyway, we will see multiple PIDs, and we are seeing multiple PIDs, and we can differentiate between who is looking at what. Oh, I see actually 3 of them. Anyway, this is of course a long list, but we are very specifically looking for the socket communication. We can see the output written out here to the file descriptor 1, which is the standard output. It's this process ID that writes it out, but I think that won't matter much. Okay, we can see some socket communication here on the file descriptor 20. Yeah, so these are the two pairs. We call a send message and a receive message. on both are on that file descriptor 20. That's a good thing. Let's take a look at when the file descriptor 20 was created. We can see a socket being created here, a socket datagram, which means that this is a UDP socket on internet, of course. It's the 6, it is actually the socket 6, I mean the file descriptor 6. Yeah, but in the next line we see that it gets duplicated to, we request it to duplicate it to the 20 file descriptor. I have no clue why they are doing this, but that's what I see here. Okay, so let's take a look at the receive message. No, to the send message. But what is this receive message? I don't even know why they are calling it here. Anyway, this is where the real communication starts. Is it readable? Yes. So we send something, and we can see google.com here. So this is a raw message that we are sending to the DNS resolver when we are making the query. And I think the message continues here. I think in total we sent out 51 bytes. So one of our main goals will be to understand these bits. So we will create a DNS query by hand, setting every bit ourselves and understanding each part of it, and also understanding the answer. This is where we got the answer. We can see a google.com here, which is promising already. Okay, I think that's enough for strace. So how are DNS documented? How can we learn about it from the source? DNS is documented in so-called RFCs, like any other internet protocols. Let's take a look at them now. So this is a page that is collected all the DNS RFCs. We can see that there are tons of them. Some are deprecated, obsoleted by newer ones. Some are not. For example, the most basic one are these two from 1987. So they are like 25 or 35 years old now. 35 years old now. But they are not deprecated. 1034 describes the concepts and facilities. 1035 is the one we will take a deeper look at. This is this describes the wire format, what we are looking for, and some resource records reflecting 1987. So some of those resource records are deprecated now, and also the label formats, and this is still valid today. If you talk DNS on as it was talked on the internet in a 1987 format, you will still get answers. That's I think that's amazing. Of course, there is the DNS is not spoken like that anymore. It got extended a bit. There is something called let's search for it. Extend DNS, EDNS, yes. We will see a bit later. So the DNS has some header, and it has some flags and status and things like that, and those are fixed length, fixed bit length, and eventually they run out of useful space there, and EDNS is a way to add more such flags to it, and they do other stuff like the whole message of DNS can be a bit longer with eDNS. We will not go deeper into that part, but this is how it is spoken today on the internet. And yeah, I think that's enough. Let's take a look at this one, the 1035, which describes the wire format. So this is how an RFC looks like. These are like small books. This one is a big one. Usually it's around 20 pages long, sometimes even smaller. But this one is a big one. So let's take a look at the contents. Data transmission order is obviously network data, network ordering, so big Indian. It will define a few things. And yeah, this will be the section we will take a deeper look at. And yeah, we will not take a look at these ones. So we will take a look at this one, and maybe where is the standard, the A record? Ah, that's funny. I think that's so basic that they don't even list it here. Anyway, before I go deeper into this document, I want to show another site. It's I don't know how to put IANA, Internet Assigned Numbers Authority. This is another authority for the DNS parameters, and you can take a look if you just want to see, for example, all the resource record types that are accepted by everyone. This is the site. So let's take a look. Where are the resource records? Yeah, not that one. I'm looking for the 100 list. Okay, I went over it. Nowhere or yes, these are them. So these are the accepted resource records. Of course, the value 1 is the A record for IPv4, a host address. And here you can see which RFC documented it. You can see the CNAME here. These are mail related ones. Some of those are deprecated and not used anymore. Yeah, for example, this one was pretty nice. Yeah, but maybe I will not. This is how you could query for, I think, the operating system and version. As far as I remember, no one answers these queries anymore, but it was interesting. Yeah, text strings are also in 1035. But there are a bunch of others. And of course, a company using DNS internally can define their own resource record types if they want to use DNS in their infrastructure, custom DNS. Okay, let's go back to the RFC 1035 and let's take a look at the wire format. So page 20. Oh, okay, I didn't speak about DNS on the high level. Maybe let's very quickly go over it, because I think there is an interesting part in that, why it is still alive to these days. So when you are making, maybe this is not the best. This is a much better other picture. So what are the players in this dance? So obviously you have the client, your host machine. And they want to know for example, the IPv4 address of google.com. And how do they get it? Usually on the host machines, there is something called a stub resolver, which is probably from your operating system, and you query that. So that's where you send your queries. It's a stub resolver, because contrasted to recursive resolvers. And let's talk about recursive resolvers. Recursive resolvers are ones that are actually doing all the DNS then. So why it is recursive? So for example, there is a domain names are separated by dots, like google.com dot, and they are in reverse order. In order to know where the com, the top level domain is located, you have to query a so-called root DNS servers. These are hardwired in every system, every recursive resolvers. You can download the actual IP addresses of these root DNS resolvers. That's the basic point. These are of course pretty stable, and there are around 13 or 15 of them. I forgot which one is, but around that number. And they are obviously not 13 machines or 15 machines. They are, but that many IP addresses. They are using Anycast, and that means that you can reach. These servers are located all over the world, and they are answering by the same IP address. And Anycast enables it that you are talking to the closest to you. So how the routing works on the internet, you will talk to the same machine that is closest to you even though there are multiple machines with the same IP address. I think Anycast is some kind of magic. Okay, so these root servers they are the ones who own where are the top level domains like com, .net or net, and the other like foreign specific, country specific names are located. And then the recursive resolver that asks these root servers, okay, where is the .com? And they get an answer. Okay, then they go to the top level domain and they ask, where is google.com? And then they send an answer back. And then the resolver goes to that DNS server that is authority for google.com, and then ask for an A record there. And then they get an answer, and that's when the recursive resolver finishes the recursive searching for that name. Okay, that was the high level. So what the stub resolver is? The stub resolver is just delegates the query to a recursive resolver. Okay. Usually the resolver you get is you get it from your ISP. So when you plug in your machine to any network by Wi-Fi or literally plug it in with Ethernet, then there is a dance with DHCP where you get your IP addresses and a bunch of other things. You get an offer from the DHCP server on that network, which contains your IP address, the subnet mask, and DNS IP addresses. That's where you get your recursive resolver. So this is on your home network. This will be your ISP's recursive DNS resolver. Unless you, of course, override this and on your host, and you say that, okay, I want to use Google's or Cloudflare's public DNS recursive DNS resolver. Then you will not send the DNS queries to your ISP. So in my case, I'm running my own recursive resolver, so I'm sending it to locally to my own DNS resolver. Okay, I talked a lot about the high level. Let's go a bit deeper. So we are looking for section 4. For some reason, it starts with the resource record. This document, and not with the So in high level, this is how it looks like. We have a header and then 4 sections. The questions section looks a bit different than the others, but they are very similar. So there will be a question and answer. This is when you get back an answer, then you always get back the question that you sent. So you know what was the question there, and these two are not necessarily there, and the header is always there. So when you are making a query, you could create a header and a question section and leave the rest empty. So what is the header section? Here you can see the number of bits. So which bit consists, for example, the first field, first 16 bits are encoding an ID. ID is just an integer. So what is this? 16-bit identifier assigned by the program. So this is an ID that you as a client send. So for example, I send 1, and when I get back an answer and it is 2, I know that this is not the answer for my previous query. So you can make a match to my queries. We can send 1 here, and we are already done. If you want to create a query with the first 16 bits, what are the others? There is one bit that specifies whether this is a query or a response. Looks simple enough. We can set it to query, and when we get back a response, it will be flipped to 1. Yes, we will make a standard query here. Yeah, and here are various flags. When we did a dig earlier, we had a section called flags, and the dig displayed these flags by these names. We will take a look at that again. I think the only important one for a query is this one, recursion desired. I think it would be interesting if we will not set it. We will set it because we will want a recursive query when we will ask it to search for google.com. This one is set by the response, I think. Yeah, this is just indicates whether the resolver can do recursive queries or not. Yeah, this is actually not true anymore. So we have 3 bits here that are not described in this RFC. They are actually, some of them are already used, and the extended DNS added a lot more. Anyway, we will just send zeros there. Our code is the default error flagging mechanism. So if we have no error, then it will be 0. If we make a bad query to a DNS resolver, then we will see some other error. There, yeah, for example, this one. If we mess it up, then we will probably get a format error. And these 4s are just they are describing how many queries we have. So how many elements we have in those sections. So we will have 1 query here. We will set 1 here and 0 for the others. So now it goes to the question section format, which is after the header. So we looked at the header, and now we look at the question format. This is important because we have to create this by hand. So this is a queue name, which can be arbitrarily long. It's not true. I think it's the length is 255, the max length of a domain name. Also, a label name must be 63 long. So the Google part must be that's the label, and that has a maximum length. Also, the total domain name has a maximum length. But anyway, every query belongs to a name, and then a type and a class. The type is basically will be the resource record type, which will be 1 for the A record that as we saw. And class will be always internet. You can have DNS on other networks, not just in. And then every resource record looks like this. It repeats the name, what in the name it belongs to. Then it also the type, which will be again the A record, so 1. The class, again, this will be internet. We get the TTL in this height is 2, so this means this 32-bit unsigned integer, which is how many seconds this resource record is valid, how long we can cache it, and then we get a length of the RD data type. Even if we don't know the resource record, we can't parse it because we can't interpret it. We never heard of, for example, this type, like we get a random number here and we don't know anything. The format still stands, and we can at least for example, print out its RD data as a binary blob and move on to the next section if we have anything. So even for unknown resource records, we can parse it relatively well. We can print out its name as a resource record name, not the domain name. We know the TTL, and we know exactly how many bytes it has. But in this case, the RD data for an A record will be 32. It will be an IPv4 address. We will take a look at that. Okay, and this is where the fun begins. But let's write some code, and we will get back to this later. I will use Rust today, but the code we will be writing will be very, very small, and it could be understandable by anyone. Really, it doesn't matter what I write. Let's call it experiment RS. Before I move on, I have a very short makefile here, so it can compile basically anything I usually use. So C, C++, single files. But this is not the main point. So I'm not using cargo, but just I will have a single file here. So as we saw that, yeah, I didn't talk about this, but DNS is usually used by UDP. We are in 1987, and UDP was the default way to communicate with the DNS resolver, and you could fail over to TCP if, for example, the message was too big for a UDP packet. So we will use a UDP socket. And now we will put together our DNS query. Maybe let me copy paste first something here. A moment. So this is the message header, DNS message header. I copy pasted this from the RFC directly, and this is what we will create today. So the first one was an ID. Everything has to be in big endian format. We will send the ID is 1. It is set by the client, and why not make it 1 then? So this is a query. And as we saw, it was the query is set. This bit has to be 0. That means that this is a query. So the next one is the opcode, which will use 0. And the only bit we set here is that we want a recursive answer. Recursive query is desired. We expect that the answer will set the recursive result available this bit to 1. We will see this later. if we didn't mess it up. We will leave that the Z bits as 0, the R code as 0. So these will be the counts of the various sections, and we will have a single section, a query section. The others will be 0, but we are in big endian format, so I will set it. So instead of writing here this, I will set it in a big endian format. Okay, let's create the query section now. So the resource record type is will be 1, which is the A record for IPv6. I always say IPv6, IPv4. This Q class is always 1. It's the internet. Now we have nearly everything. The query section needs a name. Now encoding names is a bit tricky in the DNS section, in DNS word in the wire format. Where to start it? Maybe let's open again the RFC. Okay, so normally a label is encoded in the following way. So contrary to what we see here, the first 2 bits are 0, 0, and then we get a length in the remaining bits. So that means 6 bits. So the largest label is 63. So 63 length. That means that this is where the maximum length is coming from. Now there is another way to encode labels, is that we can point to a different part in the same DNS message. I don't know the right terminology for these 2 bytes. So it can be 1 byte long or 2 bytes long. If it's 1 byte long, then it must start with 0, 0, and the next 6 bits are the length of the label. Then you can parse in the label, the bytes of the label. Then in the next byte, you look at the next 2 bits, and if it's 0, 0, then you follow the same thing. If it's 1, 1, then you actually have to look at the byte after it. You have to look at the 2 bytes. And cutting off the first 2 bits, which was 1, 1, you get 14 remaining bits. And that will be a pointer pointing to the different part of the DNS message. So it must go to a different label's first byte. So the length of Google is will be 6 letters, and now comes the letters. Then we don't have to write out the dots. The dots are implicit. This will be the com. Okay, I think we have everything to put together our query. Okay, let's create now the socket. We will be using Cloudflare's DNS here. DNS port is 53. this is the maximum length of a UDP packet, DNS packet, and yeah, that's all. Okay, let's hope I didn't make any mistakes and run it. So we created the query by hand by setting all the header, the required header bits. And we encoded our name, the queue name, the A record, the internet, and that's all it is needed. And then we will print out what we got back and try to interpret it based on what we already know. Okay, that's not a valid name. Oh, I forgot. This is the root server. So we, yeah, I forgot the dot. Anyway. Nice, we got back an answer. So let's try to interpret this answer we got back. So we got back this answer, and let's try to digest what it is. So the first one was the ID, which was 16 bits, so 2 bytes, and we got back that one. So maybe let's do this. This is the ID field, which is correct. Okay, the next ones will be a bit more interesting. So the next bytes up to here. Okay, so it is an answer. So this one should start with bit 1 because this is an answer, and lots of 4 zeros. I'm not sure about that one. And maybe hit like this. Is that correct? 128. Okay, so this looks correct. So the QR got flipped because we got an answer, and then the 7th bit is still it left it on. So that's looks okay. Okay, the next one. This is 1. Is that correct? So recursion available, that looks okay. The answer flipped that it can answer. This was left at 0 because we are talking like 1897 and this is required to be 0. That's okay. The R code 0 means that there was no error. That looks okay. No error. Okay, what else? So this one is that it repeats the queue section, the query section. This means that we got an answer section and no section for let's do this like this. No other sections. We don't have an additional section because we are not using eDNS. The DNS resolver, you have to opt in into that eDNS, and the DNS resolver answered back to us that we are from the past. But it still answered. That's nice. Okay. And now we are getting back to the various sections. For example, the next one is the query section, and it should repeat what we already sent to it. The sixth is the, so first it starts with the name and then the type and the class. The name is the google.com, and this looks okay. So first we got the, this was the bit that set the label. So if the first 2 bits is 0, and then we encoded 6 because we send next byte. So this is the Google. G-O-O, we see that's the 2-O. G-L-A. So this one was Google. Then we got the .com and the 0 after it. Okay, then we got the, this was the A record, and we got back the internet type, and here is the data section. Wait a moment. No, this is the answer section, the next one. So this is a resource record. A resource record starts with a name. Yeah, there will be, let's copy paste it again from the RFC. So this is how a resource record is encoded, and this is the last line we have to understand here now. It starts with a name, and we don't see a google.com here because it used message compression. Now this means that the first 2 bytes should be a pointer, except it starts with 2 bits. We should cut that off, and it should point to actually here. So what we are looking for, so to this byte from the start of the message, which bit is that? So this would be 0, 1, 2, 3, 4, 5. So I think it should be the 12th bit, and that's it. It is the 12th byte. It points from the start of the message to the 12th byte. So this is a pointer. This is google.com, because this one starts, it looks like this. How many zeros? Yes, one less. Okay, amazing. Okay, the next one is the type. This is the A record. The class, which is internet. And here comes the TTR. Okay, but as the length is the next 2 bytes, and as it said, we have only 4 bytes, which is the IP address. Okay, amazing, it worked. Let's quickly, never mind. Okay, let's recap what we did. We created a query by hand by setting up all the bits that are needed, encoded the name, which was the most important part. We created a query by hand. We created a UDP socket to Cloudflare's open recursive DNS resolver. And then we sent a query to it. We talked DNS as in 1987, and we printed out the answer. And then we looked at the bits of the answer and understood all parts of it. The ID, the error fields, the flags, the various sections. We interpreted all of them, and also found that the DNS server created a message compression and did not repeat it to google.com in the answer section, just by using these 2 bytes, by making a pointer to the query section. By the way, this makes it a bit harder to create a code that parses DNS responses, because you can't because the various sections are not self-contained; they are part of the bigger message. You can imagine that you write a parser code for it, and then you can just hand it off to smaller functions, because you have to keep the big picture all the time. But that's just, you can just refer back to the whole message, or you can create. I'm a bit ahead of myself. Okay, I think I will stop here. If you want to, let's take a look at again the digs output. So now we are understanding all parts of this. So this is the header section. We have this is a query. This is basically the first bit. But it's opcode. Oh no, this means that this was a normal query. Then no error, which was encoded in 4 bits, if I remember, or 3 bits. I already forgot. We sent this ID. I don't know. The dig doesn't use. Maybe this is a random. Then we see that which kind of flags were set and how many sections we got. Yeah, dig uses eDNS, so it's actually sent an additional field. Then yeah, this is the ops section. This is the eDNS part, which we did not set. And here we see the google.com repeated, the query we sent. Here we see the answer, TTL, internet, A-record. And we don't see the additional section listed here, because this is basically this one. And this was actually bigger than... No, this is just a flag. What is the biggest one? Never mind. Yeah, I think that's all I wanted to show today.